So I thought I'll give you a little bit about the work we're doing trying to understand the polarized emission from TDEs. And I know people don't usually think about polarization, and for good reason. This is not an easy thing to do, but I hope I will convince you that it's really kind of worth the hustle. And we really get a lot more information than you would normally do just by looking at photometry or even spectroscopy. The problem we're facing, apart from we only have just a couple of measurements of TDEs, is that we don't really have a good theoretical understanding of what the polarized emission of these objects should look like. But we can leverage on a couple of decades now of experience for other accreting supermassive black hole systems. So if you look at what we call the radio quiet, AGN, here polarization is very much dependent on the inclination of the system. So we think the emission is pretty much coming just from the accretion disk and the surrounding structures here, right? So if you're looking at events face on, like this one here, you basically don't get any polarization. We get maybe a couple of %. Usually those are unpolarized. If you start to sort of change the inclination and you move towards the edge-on systems, now you start to see a little bit of polarization, but at maximum that should be maybe about 10%. This is kind of what you see here. And a very characteristic of the systems is that the polarization angle that we see is fairly constant over time. This is because this comes from scattering, and you have a fixed scattering geometry that doesn't really change. Now, if you look at the radio loud systems, or particularly blazars, which is my favorite thing, here the emission is coming from the jet. So this is singleton radiation. It's highly variable, highly polarized, and you can see here a couple of examples. And in particular, this is a polarized flare we discovered very recently, where at peak you go up to 47%. Now, this is kind of our record holder at the moment, but getting 20 to 30% polarization for blazars, this is kind of another just another Tuesday. It's not really any significant event that we'll talk about. A very interesting phenomenon we see in these sources, and we don't fully understand where this is coming from, is what we call the rotations of the polarization angle. So this is what you see down here. So at some, when you observe the source, the polarization angle is at some level, and then suddenly you get these monotonic changes that can go over 180 degrees, and then it just goes back to fluctuating, happily at some other value. So before we started getting into this business, there were pretty much 6 observations of TDEs in polarization. Most of them were, single observation. Some were just upper limits. A couple were serendipitous observations, so we didn't really have a lot of information on that. And every time you had more than one, there would be a trend of having higher polarization at earlier times that would just disappear very soon as the event progressed. Which is not really a lot to go on, but based on that, we could deduce that we expect for optical TDEs to have maybe 1 or 2% polarization. This will be analogous to the radio quiet systems. And then the jetted TDEs have higher, maybe 7 or 8% polarization, which again will be similar to what we see in blazars. So you can imagine our surprise when we observed our very first event, which was called 2020 MOT. This is what you heard earlier that had this big infrared excess, which I actually did not know about until an hour ago. So thank you about that. So what you see here is the ZTF light curve at the top, and then the middle panel is the polarization degree, and the bottom panel is the polarization angle. So we see this polarized flare that is offset from the main peak, and at maximum it's 25%. And then when that happens, we also see this change in the polarization angle. So my immediate reaction to this was that we're looking at the jet. This is what jets do. But there was no jet in the system, or at least one that we could find. We had radio observations and X-rays, both early times, several months after. When you look at the spectrum, apart from the classification lines, there wasn't really anything there. And then every other metric we used to compare to other TDEs was telling us that this is a very standard, boring optical TDE. So now it really becomes a problem where that 25% polarization is coming from. And you heard a very lovely introduction to this earlier in Gary's talk. I'm sure we'll hear a lot about the different models, and I understand there are differences, nuances, and all those things. I'm broadly separating things into the reprocessing and the shock models. So in terms of the polarization properties, when you have these reprocessing models, we expect this to come from electron scattering. That will give you maybe a few % polarization. If you're looking at direct emission from the accretion disk, that should be even worse. And every time you sort of introduce some, layers, some atmosphere or some symmetry, let's say, in your system, you pretty much kill the polarization. So you cannot get 25% out of those things, at least the simple versions. And one other thing we cannot really explain is the change in the polarization angle, because all those models also have some geometry to them that is not supposed to change. Now, in terms of the shock models, we know that there should be magnetic fields there, at least at some level. Shocks will align those magnetic fields, and aligned magnetic fields naturally give rise to polarized emission. Now, we don't really have any simulations or any models on these shocks that will tell us what we would expect in polarization, but there are other metrics that we can sort of use and figure out whether this actually makes sense or not. So let's entertain the idea that we are, in fact, looking at those shocks. Then we can estimate the mass of the black hole and the star that you see here, and then you can plot out multiples of what's called the timescale of the orbital timescale of the most bound material. So what we think might have happened here is at t equals 0, you disrupt the star, gas flowing around the black hole, as you've heard earlier. As you go through the pericenter, you form the first shock. That shock should be responsible for all the rising part of the emission until the peak. The peak should happen at 1.5 times that orbital timescale, and as you can see, that actually matches the prediction fairly well. At peak, you have the outer shocks forming. These are not very strong in the beginning, but they grow stronger over time. And at some point, we expect them to be the dominant emission component in the system. And then where you're 3 times that, or the timescale, or away from that, you sort of expect the stream has circularized, the outer shocks still are the dominant component before the accretion disk fires up, and shock 1 has sort of dissipated away. So when we had our first observation, we think that we're looking at the first shock, or at least the period where the first shock was the dominant component in the system. That changed sometime in the 20 days between our first and second observation, and now we're looking at the outer shocks. That's why we see much higher polarization, but we also see the change in the polarization angle. And this is what's telling us that we're now looking at something else that we were doing before. And then, as expected, we should keep looking at these outer shocks, and in fact, the polarization angle doesn't really change over time after that. So that seems to match fairly well. And now the question becomes, is this a standard picture for all TDEs, or we're looking at some peculiar or some weird event? And the truth is that so far MOT seems to be unique. So here's a collection of some optical, some relativistic TDEs, and a few other things. And as you can see, everything is sort of below this 10% line, which is what we kind of expect from these accreting black hole systems. There's only MOT that really goes beyond that. So we've been trying to get more observations, hoping that we'll see more of this, highly polarized events, and then we can compare and see what are the differences, what are the similarities, and whatnot. Unfortunately, we've not been very successful in doing that, but that doesn't mean that we've seen some very interesting behavior, which I'll tell you about now. So a second source that we've been studying, and we had the paper in archive just a few days ago, it's called 2022 FPX. And we think it's a TDE, but it could be something else. And the reason I say that is that it shows some very peculiar properties. And the first one is, of course, its light curve, which, as you've noticed, this is the ZTF light curve, this is the SWIFT, and it has been a very slow event. It's almost 2 years that's going on, and it's still, not over. The baseline is about a magnitude lower than that. So it's still going pretty strong. Another very interesting property is the spectrum. So we see this high excitation coronal lines. So we think it might be one of these extreme coronal line emitters that you've heard before. These are typically associated with AGN activity, and you would need a lot of extreme UV and X-rays at early times to make them. As you can see from the SWIFT light curve, we pretty much get upper limits. And when we look at the pre-TD host magnitudes and we do modeling of the galaxy, there's really no evidence of any AGN activity before that. The light curve is fairly flat. We don't really see. So one interpretation we've been toying with is that this might be a Bowen fluorescent flare, which you also heard in the previous talk. So here is basically the light curve of a coronal line emitter in green, FPX is in blue, and then red is one candidate Bowen flare. So as you can see, the shape of the light curve and the duration kind of matches more the Bowen flare. Here, when you have this sort of bump, we do also, this happens for us when we have the X-ray flare. We do see a bump a little bit in optical and UV, which is obviously not as pronoun in the Bowen flare. But when we look at the X-rays from the candidate Bowen flare, we don't see anything when that bump happens. So nothing really matches, exactly. So it could be a case where you have all of those things happening together. So we're not entirely sure. We're sticking with the TD interpretation for now. What is more interesting is actually the polarization behavior. So here's the polarization degree and angle. This cluster of points is around the optical peak, and this cluster of points is around the X-ray flare. And this is the first time we see flickering in the polarization. So usually it would be some monotonic change. Here we've seen this up, down, and when this happens, we also see this very nice rotation in the polarization angle with a sudden jump back up. When you look at the X-ray flare, basically the source is unpolarized. We get 3 sigma upper limits of 0.3, 0.4%. So again, one of the interpretations is that we're looking at this shocks. So if you remember, around the peak, we expect all the different shocks to be forming. So you could imagine a scenario where you have different emission components firing up, and then that will give you sort of the changes in the polarization that we see. And then later on, you pretty much circularize the gas, fire up the accretion disk, and as we expect, the accretion disk emission is not polarized. So that again seems to match nicely. One other interpretation we've been toying with, just because it's fun to do, is that you have a very compact, clumpy torus in your system. So these are simulations that have been done for AGN, and this is again polarization degree and angle, but this time versus the inclination of the system. So one value of the inclination will give you one value for the polarization parameters. But you can imagine that you have the inner accretion disk that's precessing, and that might give you this polarization behavior, and will also give you this movement of the polarization, the angle with a sudden jump back up. And you only have to move up maybe about 20 to 30 degrees, so it's not crazy. We don't see any pulsations, we don't see any QPEs, anything like that. So we cannot put really any meaningful constraints on the precession time scale. If you assume that by the time that we don't see any polarization, the accretion disk is aligned, then you can put maybe some upper limits on the alignment time scale of that, which, given the black hole mass estimates that we have, it seems to work, but it would require a very low spinning black hole. So you need a spin of about 0.1. So it's not crazy, but at this point, these are just hand wavy back on the envelope calculations that we're doing just for fun. It's not, we cannot really say too much about that just yet. So finally, let me tell you about what we've been working on now, which is a sort called 2023 CLX. And basically, this is the first time we see similar behavior to MOT, but at a much lower polarization angle. So again, you see, brightness, polarization, degree, polarization, angle, and we see sort of this rise in polarization, which is again offset from the main peak. And when that happens, we again see this change in the polarization angle and then remaining constant over time. So if you compare that with MOT, we think we might have caught this rising part. We have much better sampling for CLX, but unfortunately we could not get the other side. So we don't have any observations here. So we don't really know, where the polarization rise stopped or where it actually, go down as we've seen before. But as you can see, you start with a different polarization angle and then you just switch and this stays, stable as the polarization sort of rises. And actually this change is fairly comparable. In CLX, we just see 10 to 20 degrees more change, which is not really a big thing. So we could be looking at shocks again, it could be something else, but it's definitely exciting that we get some consistent behavior sort of for the first time that might point to some common underlying mechanism. Like I said, we just started working on this, so I cannot say too much, but it looks very promising. So before I finish, let me advertise that we're organizing a TDE nuclear transient meeting in Crete. It will take place 2 to 6 of September this year. The abstract submission has opened and will continue until the end of May. So you have a month and a little bit more to submit your abstract. So there are really no excuses not to do it. You can find a lot more information here, but I'm here as well, so you can just come grab me and ask me about that. So just to summarize, as you've seen, TDEs can be highly polarized, and we don't know where that polarization is coming from. We think we're looking at shocks, but this is at this point pretty much in lack of a better model. So if you have ideas, if you have a model that you think fits better, please let me know about this. We see a lot of polarization variability, which was not really expected. And what seems to be sort of an emerging trend is that we see these changes in the polarization angle that need to be explained. So whatever model you subscribe to, it cannot be a very simple, symmetric, uniform thing. It has to be dynamic, it has to change over time. Otherwise, there's no way to get the polarization properties that we see. Thank you very much.
Okay, thank you, Yannis, for those exciting results.
Hello, thanks for the nice talk. Yeah, I have a piece of information for FPX. There's also a dust echo, but it's also variable in the infrared before the flare at a very low level. So it's definitely some AGN activity or beforehand, but it's a giant echo. So, but I have a question about the MOT.
Okay.
So I was just speculating, putting two pieces of information together. So we have the I-band excess that we heard about, and also this polarization. So could you have some asymmetric dust distribution that scatters the light, and then you get this I-band excess? Would that be existent also with your polarization, or doesn't give the right level?
So usually the dust-induced polarization, even at the heart of the galactic center, only gets a few percent.
Okay, so
it's not really. And also you will need that dust to actually to move to change the polarization angle, because that's another scattering effect, right? So it's hard to like I said, I won't claim that we know the answer, but definitely any simple scattering thing is not working for that. But yeah, I have not thought about the infrared excess because, like I said, just found out an hour ago about this. But it's certainly very interesting.
Thanks. Could I ask one technical thing?
Yeah, go ahead.
Yeah, I was just curious for the host correction.
Oh.
That of course boosts it quite a bit. But just to be sure that that's real, could we just observe it now and see that it's gone?
The polarization?
Yeah. I mean, because it increases very much after you make the correction, and that's what makes it special, right?
Well, yes. First of all, let me tell you that even in the observed polarization, we get 7%, which will still be higher than the electroscattering models.
Okay.
Even without making any correction. That particular correction has haunted me a little bit. I have lost sleep over it. But we did it in so many different ways using different data. Let me just say that there is no effect that we know of that will cause this to not be real. We have not observed the source again. I think there were some observations taken by the people in Finland after some time, but I've not heard of any result. But definitely something that I need to look at. Usually what we think we're looking at is sort of a face-on galaxy, or at least we did not, when modeling the galaxy, there was no evidence for any significant inclination. And for normal galaxies, we don't expect more than 1% polarization for those, but you never know.
Thanks.
Okay.
Go ahead.
Go ahead.
Oh, okay. So yeah, I'm also curious about had similar question as Short. So you assume the host, meaning along the line of sight, has no polarization, right? And the host meaning that you go from your black data point to the green data point, right?
Yeah.
At the peak polarization time, you assume that the host contribute quite a lot of light, large fraction of the light, but it's unpolarized. Is that understanding correct?
Yeah.
I see. So it would be nice, as Short was suggesting, to go back and see if actually the host galaxy, because now this transient has faded, to see is actually the host galaxy is actually unpolarized or not, right? So actually my question is, if it is 25%, it's really difficult because you have a thermal spectrum in the optical. How is really I don't know if you have any shocks or any strongly magnetized shocks that I am not aware of any case where you can produce a thermal spectrum while having 25% polarization. Yeah, that's hard to believe.
No, I believe you. It's not one. We don't have a good, like I said, we don't have a good theoretical understanding of what.
That's
we
right.
don't have a good protection. The models we've been considering is that you might have a thermal synchrotron happening, and that should be, I mean, at least theoretically, could be up to 100% polarized. You could have one other thing we thought about is that you may again have the shock, but then shock changes the viewing angle to the line of sight, because I mean the whole thing is sort of maybe moving around, and that also changing in the viewing angle could give you large variation polarization. We don't have a good explanation for this, but like I said, all the other scattering geometries, nothing can work.
That's right. That's
in this
right.
case. So
yes, thermal synchrotron is also not gonna give you a thermal. Really, even if the underlying electron population has a thermal Lorentz factor distribution. So it's kind of strange. It's very puzzling. Thanks.
Okay.
So continuing the theme, this is super interesting. Can the spectrum be fit by a model in which you have X percentage synchrotron that's very highly polarized and 1 minus X thermal that's unpolarized?
or when you're looking at when you're talking about the spectrum.
Yeah, because I think that's really there seems like no way of getting this other than to start invoking synchrotron. And so the question then is really, is it consistent with the other data on the SED?
So for the SED, basically we could not differentiate really between a black body and a parallel. So there were some cases that it looked to be more consistent with a parallel over time. Sometimes you could fit a black body there, but we really could not. We didn't have the power to tell that. But the spectrum does look like a parallel, that you can say there is some synchrotron emission there. But
All right, thanks.
My questions are on exactly the same theme as well.
Okay.
But maybe I'll take one step further and ask, are you aware of any spectropolarimetric observations of this object around similar times?
No.
Okay.
No. We actually did not, I think that was kind of the problem. We did not really expect to see things really that. It was more of a, oh, this happens. Let's see, if it shows any polarized emission. That's why we did not really, we just had like a month gap between the observations. We were not really paying too much attention to it. So that's on us. That's on us. But
I'm just curious about maybe someone who knows what the optical spectra looked like at this time.
So actually, okay, there was really no lines in the optical spectrum other than classification lines. There was not really anything,
I guess where I'm going with that is I'm wondering whether sort of the excess could be due to lines, or at least associated with lines for some reason that I'm not.
The excess of the polarization? Oh, that would do you the opposite effect. Because, those are excitation lines. They should not be polarized.
It shouldn't be, right? Yeah.
So that will drop your polarization if there was anything there. But the spectrum did not show any line, especially in the R band. You don't.
Yeah. Exactly right. Yeah. It's nothing particular.
So no, not really.
Interesting.
Hi, great talk. About the FPX, 22 FPX, can you go back to the optical spectrum?
Yeah.
So besides of the early time infrared variability that Short mentioned, this like the lines are pretty narrow, right? This is not commonly observed on TDEs, right?
Well, they told me, because I'm not an expert in spectroscopy, I told them they're still consistent, but they are on the narrow side.
Yeah, to me it looks more like a narrow line here for one, for example. Then, yeah, and they're persistent. Yeah, so that doesn't look at all like a TDE.
I mean, this is not like one-to-one, but the difference is that there really is not iron 7 as the coronal line here. It's the coronal lines here are iron 10 and iron 14. And if you were to do like a BPT diagram, you're going to also not be, like, you're going to be convinced it's not an AGN. So that's kind of, like, yes, the lines are reminiscent of the Seiferts, but without the strength and without the iron 7.
Yeah, I'm talking about the H alpha. The H alpha is much narrower than any TDEs that we observed.
I don't think it's usually proposed that the H alpha is part of the transient, though, for what it's worth. Yeah.
Thank you.
Actually, I had a question. Right, so for 22 FPX, I saw in the paper as well that MOSFET was run on it to try to treat it like a TDE. But like you said, it's a pretty long-lived light curve. I'm just curious if you could speak more on, if it's not a TDE, since it's so odd, what else could possibly explain it?
Yeah, I mean, like I said, we not have a good handle on what it is. It's definitely, having this extreme coronal lines would put it in this category of transients. We kind of like the bound flare interpretation more, but we're not, like I said, nothing really matches exactly. So there's not something that we can say, oh, this is definitely one thing. It could be that actually, given the uncertainty we have in all those things, and as you've heard, that this bound flares might be related to AGN, which might be related to extreme coronal lines, it could all be the same thing, right? We're just seeing different properties pop up. But yeah, and that's why we also sort of toyed with the compact clapping torus interpretation, that we at least have some simulations from AGN we can play with. But like I said, we're sticking with the TDE interpretation until told otherwise.
Okay, maybe I'll ask a final question. What do we need in order to turn these observations into physical parameters for these systems?
Oh, yeah, okay. We need models. We need simulations. We need people in the audience to include magnetic fields in your simulations, do radiative transfer, do all the hard work, and, give us something real to compare with. That's what we need, pretty much. I mean, we're getting the observations now, and, as the rate of TDEs goes up, we're going to get more polarization observations. So we need the theory to back us up here. So please do that.
Okay, let's thank Yannis, Erica, and Yair. and we will reconvene in 35 minutes for the next session.